Okay, so it's my pleasure to introduce Max Engelstein from MIT. We're going to talk about the role of energy in regularity.
Thank you very much. And thank you all for coming. It's great to be here. I'm from New York originally, so it feels like we're home. So maybe some standard caveats here. You might not be able to tell, but my handwriting can be terrible. So if I write something that you can't read, just yell at me, and I'll try to rewrite it. And if I write something that you can read, but you still don't understand, also yell at me, and I'll try to re-explain it. Okay, so let me maybe start this talk with a prologue, which is sort of 100 years of the calculus of variations in, I don't know, a quarter of a board, or something like this. So say we're trying to minimize some nice energy. You can think the Differential energy, which is the gradient squared. You know, U maybe has one derivative, which is square integrable, but if you would rather U be in C1, I'm happy to do that for you. And U is equal to some nice function phi on the boundary of the ball. This happens on the boundary.
This is like a colloquium, right? So it's supposed to be like colloquium.
Yeah.
So H1 means the space exactly where that thing is defined, right?
Yes, that's
You
exactly
don't know
right.
that notation.
Yes,
Right.
sorry. Or W12
That's
if
what
you
you
really
said.
like it. But basically, the weakest possible space in which this makes sense, that's the space that I want to minimize over. Exactly. Okay, so if it's a minimum, then certainly if I compare it against any sort of perturbation, I should get something bigger, right? So in particular, if I take the derivative of this in epsilon and set epsilon equal to 0, phi is something that doesn't touch the boundary conditions. So say phi is C infinity, if you like, has infinitely many derivatives, and it has compact support, right? So that means that it doesn't touch the boundary. This should be equal to 0, right? Or in other words, this inner product is equal to 0. That's just algebra. If U satisfies this, we call it weakly harmonic. And it's kind of a minor miracle that weak harmonicity actually implies that the Laplacian of U equals 0, and U is analytic. So what happened here? We started minimizing in a space which was super weak. These functions might not even be continuous. And in the end, we got an analytic function. And this self-regularization is sort of maybe a triumph of 20th century PD. It's the culmination of a lot of work. Not for the Laplacian in particular, but for a huge class of linear functions.
In the interior.
In the interior, yes.
Not
All of this is
boundary.
happening in the interior.
Boundary
So,
values are not.
If you'd like, on any set K, which is compactly supported inside of U. Yes, thank you. But now, so what have we really done here? We've said, hey, U is a minimizer, so that means U is a critical point, and then we got a PDE. But I want to present two situations in which understanding critical points is a little bit misleading. It doesn't actually tell you the full story. So maybe the first situation is, say we want to look at area minimizers. Right? So I want to look at some set which has the least possible area out of all the other sets which agree with it on the boundary of some ball. Or something like this. It turns out that if you suitably weakly define what it means to minimize, that this triple junction, this is the best picture of a triple junction I've ever drawn in my life. Here we go. That this triple junction is an area minimizer. But now, okay, you try to play this game. You do the triple junction plus some sort of compactly supported thing. And soon you'll find that around this set of singular points, it's not so clear what type of PDE you should be satisfying. Right? So maybe this is the first sort of moral. Near singularities, the critical point equation is ill-defined. And now I want to look at a second example. It's going to be a lot like this example, but instead of looking at functions whose target is R, I'm going to look at functions whose target is S2. Okay? So my energy is du squared, where now u goes from the ball of radius 1, that lives inside of R3, to the sphere. Okay? And I'm going to assume that u is a critical point. So it satisfies an equation like this. So if you don't mind, I'll do a little bit of bad board work. U plus epsilon phi. Phi goes from R3 to R3, and phi is compactly supported in the ball of radius 1. But I want this to still have image S2, so I'm going to just do a projection. This is the nearest point projection onto S2, which is well defined as long as epsilon is small enough. Okay, great. Squared d epsilon, epsilon equals 0. And something which satisfies this for all such phi is called a weak harmonic map.
So that satisfies that equals 0.
It satisfies this. Whew, satisfies this equals 0 for all phi. And now here is an amazing theorem of Tristan Riviere from the early 90s. Riviere. Really nice. For all boundary data, so in C infinity of partial V1 to the sphere, there exists, I want phi1 to be non-constant. There exists a u.
What? To be what?
Non-constant.
Oh.
I'm sorry. There exists a u which goes from B1 to S2, which is weakly harmonic. So it satisfies this. And u is discontinuous everywhere in the closed ball. So here, we started with minimizers, we reduced to critical points, and we got regularity. Tristan tells us that if you try to play the same game but with a curved target, you immediately run afoul. This is perhaps the second simplest situation that you could think of, right? And you immediately see that not only do you not get analyticity, you don't get continuity. Okay? So, sort of the second war.
Minimizer unique? It's not unique. Right?
This is not a minimizer. It's a critical point.
Oh.
And that's very, very important. So actually that leads me exactly into my set of questions. Question 1.
Well, here it was the minimizer though, right?
It's because here the problem is convex. So being a minimizer or being a critical point is the same thing. Here the energy is convex, but the constraint that you map into S2 is no longer convex. And so there are critical points that are not minimizers. But that's sort of exactly one of the points of the talk. So question 1 is, what tools do we have to understand minimizers without PDE? And maybe question 2 is, when are critical points, and I'll put this in quotation marks because there actually won't be an energy, regularizing like minimizers should be. So there's these two questions. You should think of the first question as being motivated by this first example, and the second question is being motivated by the second example. And hopefully I'll have time to talk to you about both of them. Okay? Great. So maybe I should take a second here. Are there any questions so far? Usually people have a lot of misgivings about this example, but maybe you're just willing to take my word for it. It should be completely shocking. I am very surprised by it. Okay, so part 1, which maybe we'll entitle Variational Tools. So there are 100 different problems in the calculus of variations, and it would just be completely useless for me to try to talk about all of them. So let me specialize to one. Let me specialize to maybe the most classical, which is minimal surfaces, right? So what do I mean? There's a lot of technicalities in sort of defining a space which is broad enough that you can actually solve the minimization problem, and so on and so forth, right? I mean, the idea is that if you just restrict yourself to really classical manifolds, there'll be some things that you aren't able to find solutions for minimizers for, and so on and so forth. So you need to find a weak notion, and so on and so forth. Don't worry about any of that. You should just be thinking about classical manifolds, except maybe they have some singular points like this. Okay? So we say that M is a minimal or a area minimizer if the area of M intersect any ball of radius r around a point x is less than the area of some other circle intersected this ball of radius r around a point x for all s such that s equals m on the boundary of the ball. Okay? So if you have the same, I would call it a trace because I started from functions. Oh wait, sorry, what was the word you told me to actually call it?
Cross-section.
Cross-section. If you have the same cross-section in the sphere, then you should have less area if you're the minimizer. Okay. And actually, I don't want to study minimizers because minimizers satisfy some PDE in a weak sense. Their mean curvature is 0. And I don't want to accidentally use the PDE somewhere. So what I'm going to study is almost area minimizers, where instead of requiring the strict inequality, I'm going to allow myself an error. Now, I want this C. So if there exists a C greater than 0, alpha in 0, 1, and M lives inside of R, let's say, M is an n-dimensional manifold. Okay? So if the area of M in a ball of radius R is less than the area of S, plus a term that goes to 0 faster than the area does. And if you'd like, you could think about this extra error as being physical.
I mean, a flat ball would be just r to the n.
Yes, a flat ball is just r to the n, so this is r to the n plus a little faster. I could pick any Dini modulus of continuity here, so it's integrable at 0, but this is too much, right? Alpha is fine. You should think of this as sort of being physical if you'd like. You know, minimal surfaces are supposed to model certain actual things in real life, like a soap bubble floating through the air. But in reality, there are more things in life than surface tension. There are things like gravity and lower order forces. And these lower order forces can live inside of here. Okay? Also, minimal surfaces are really useful for constrained minimization. If you want to fill the room with a bunch of bubbles of area 1, then they would actually satisfy almost minimization as opposed to minimizing. Each individual bubble would be an almost minimizer for area. And also, they don't have a PDE, so I like them. Okay? Great. And so, fantastic. It's perhaps surprising that almost the minimizers, at least the first order, have the same regularity as minimizers. So here's a theorem, which I'm not going to attribute to anyone, because no matter who I attribute to, people will get mad. If you got your PhD at Princeton, you'll insist that it's Almgren. If you're Italian, you'll insist that it's De Giorgi. These are the only two groups that really insist. Everyone else is just mad, but silently mad, so it's okay. So there exists a delta, which is going to be a flatness parameter, such that if in BR x0, where x0 is in M and R is greater than 0, M is contained in a delta R neighborhood of n-plane, then in BR over 2 x naught, M is the graph of a C1 beta function. And in this theorem, M is an almost minimizer, and delta and beta depend on n, the ambient dimension, and C and alpha. Okay, so let me draw you a picture.
Right, so you assume that M is an almost minimizers, and that's the conclusion.
Yes, so sorry, M, oh my god. Today I was supposed to give my last class of the semester, and I'm importing all my bad board work from that class into this talk right here, so I apologize. So here's the picture. Here you have your almost minimizer. Who knows what it looks like? But say, at this point, and at this scale, you're contained inside of a delta R slab. Then, if you just inch in a little bit, you're actually the graph of a smooth function. Okay? This is a phenomenon known as epsilon regularity in minimal surfaces or in the calculus of variations. And it's this idea that if you're flat at some scale, you should be smooth at all the smaller scales. So let me give you a sort of hand waving.
Delta small?
Delta is small, yes.
You don't say that, do you?
No, but I mean, theoretically, delta could be big. In every possible instantiation that I know of, delta is small.
I just wanted to
I'm sorry. You're absolutely right. Maybe I should write it this way. There exists a delta, maybe I'll call it delta sub n, such that if delta is less than delta sub n, and you're contained in this delta R neighborhood, then the following is true. Right? So there's some sort of threshold. This threshold is small, and then, yeah. Maybe that's better. Okay, hand wavy proof. If you're flat, then somehow you feel like you're kind of close to being a plane. And if you linearize the energy, the area energy around a plane, you basically get this energy. And then you should expect that you have some sort of smoothness because you're basically being governed by this. This is, I mean, there's a lot of technicalities, but this is the idea. Okay. But what if you never get flat? Okay? Here are some examples. Oh, this one's pretty good too. This is surprising. So here are 3 examples of minimal surfaces for different notions of what class of thing you're minimizing over. And if you're centered around the point on this line, it doesn't matter how much you zoom in. You'll never look like you're squished between 2 planes, right? Because these are sort of cone points. And similarly, if you're trying to enclose 2 different areas in what's called a double bubble configuration, then around this point, you'll never look like you're contained between 2 points. It's not clear from my picture, but these come out at 120-degree angles. So they're never contained inside of a little flat.
Locally, it looks the same as the other one.
Yes, indeed, and that's going to happen in 5 seconds. And then, because I'm at Stony Brook, I have to put up this example. This example is called the Simons cone, after Jim Simons. And it was proven to be an area minimizer when n is greater than or equal to 4. It's a critical point for area when n is less than 4, but not a minimizer. I can't draw in R8, so I omitted the picture. I'm sorry. Okay, so yes, let's look at what happens at this point. Sorry, did you have a question? So I'm going to take this point, and I'm going to zoom the picture out. And exactly as was suggested, infinitesimally, you look like this, but in reality, my surface is going to look maybe like that, right? So I don't know why I did this, but I switched. What was white is now yellow, and what was not there is now white. So I apologize.
The yellow and the white looks the same.
Oh, can you just tell me the difference? Okay. Sorry. So if this is x0 and this is r, then, and this whole surface was m, then this is m minus x0 over r. Right? That's what I'm drawing here. I'm zooming in. So in a perfect world, here's what we want. That m minus x0 over r converges to some m infinity. This is going to be a minimizer, and it's actually going to have some extra structure. It's going to be a cone, but maybe that's not so obvious. And then we'd like that there exists a map phi, which goes from B1 to B1. Let's say phi is smooth. And
M is two-dimensional, right?
actually, I'd like you to think, so, okay, yes, M is two-dimensional. It's two planes
So
coming
the
together.
picture here is like a section.
Yes, it should be this picture, but as I promised you, it's getting worse.
So
Yeah, I'm looking at it head
you
up.
have to slide that Y back and forth.
Yes, exactly. I'm looking at the picture head up. And these curves could depend on the distance you are out of the board. What I want is that the image of M infinity underneath this map parametrizes M minus x0 over r for some r, let's say, for r. Okay? So in general, I want the local geometry of this soap bubble to be determined by the infinitesimal behavior here. This is a very important question, not just in the calculus of variations, but also in applications to things like geometry and mathematical physics. Somehow, if you want to use your minimal surfaces to tell you anything geometric, if they start to develop singularities, you want to be able to still understand the geometry of your space in a neighborhood of these singularities. And this is sort of one way of understanding this. Okay? So this is what we like. But then, there's a big problem. So what's the big problem? M infinity comes from compactness. So you can guarantee that some sort of limit like this exists, but only up to subsequences, right? So, i.e., there exists some rj's which go down to 0, such that m minus x naught over rj converges to m infinity. And what if m infinity depends on the sequence rj? Right?
So this means you're taking this limit, and then M infinity is kind of, the limit is M infinity, and you want to claim it's modeled of the smooth map of bijection.
Yeah, sure. Smooth bijection. I even want it to be bi-smooth, so biholder or something like that. But there's an even earlier problem, right? This M infinity might not exist. In other words, the sort of first term in the Taylor series expansion, if you'd like, might not be unique. It might not be there. Okay. So whenever I give this talk to people who don't work in regularity, they immediately think that I'm just sort of drumming up business. This can't be a real issue. You must always actually have uniqueness of singularities, right? But there's a beautiful example by Brian White where he looks at minimizers to the harmonic map equation. But now U goes from B1 inside of R3 to N, which is a C infinity manifold. And U has continuum many blowups at the origin. So if you do this exact same procedure, you zoom in, zoom in, zoom in, zoom in, zoom in, you get infinitely many different sort of M infinities, depending on which sequences you go in on. This is key, C infinity, as opposed to analytic. It's because if you have a gradient flow of a C infinity function, it doesn't have a unique limit point. You can approach a whole level set. This is called the goat tracks example. I don't know much about goats, so I don't know sort of what's going on here, but the idea is that your gradient flow can get closer and closer to some sort of level set here, but never actually reach something. This is impossible if your gradient flow is generated by an analytic function. Okay? So we'll talk about that sort of in a little bit. Okay, so uniqueness of blowups is a real question, right? It's something that you actually need to verify. And you certainly can't prove this without showing that M infinity exists. So here's a theorem. It's by myself, Luca Spilaro, who's a postdoc at MIT with me, and Bozidar Velichkov, who's a maitre d' conférence at the Université Grenoble-Alpes. So let M be an almost minimizer. Let x0 be inside of M, such that there exists some sequence of rj's going down to 0, such that n minus x naught over rj converges to M infinity, and M infinity has an isolated singularity. So you should be thinking about M infinity as looking like this, which has an isolated singularity at the origin, as opposed to like this, which has a whole line of singularities. Then M infinity is unique. That is, M minus x0 over R fully goes to M infinity. And with a C1 plus rate of convergence.
Can you prove this in families?
So you're saying, can I prove that the
Family
continuity
of
is...
problems, and you smooth down parameter, and then proving each fiber?
Yes, so I think you can do this. No, it's a little bit tricky. So really, all the constants here really depend on this isolated singularity. I mean, there's something very qualitative about it as opposed to quantitative.
It's not constructive.
No, it is a constructive. Well, it's a little complicated. I can talk about it in a second. Maybe let me make some remarks. If M is a minimizer, then this was actually proven by Leon Simons and Allard Almgren in the early 80s. These are both 40-plus page annals papers. This is 18 pages. So we sort of get both in one blow. Of course, they actually prove it for critical points. We prove it for almost minimizers, right? So our results are disjoint. They don't overlap. Or they do overlap, but they don't. One doesn't subsume the other. And the technique is completely different. They really use the PDE here. They try to parameterize the surface over the blowup, argue that these yellow squiggles should satisfy some sort of PDE, and then they do Fourier series, essentially. I don't want to minimize it. These are beautiful, beautiful papers. But that's what's going on. We don't use the PDE at all, because we don't have a PDE. We use a purely variational technique, which I don't think I should get into too much, but maybe I'll just say in words. There's a beautiful idea of Ernst Reifenberg, who died in 1964, called the epiparametric inequality. And it talks about what the energy of minimizers with extra structure look like. In this case, minimizers which are cones. And what we did was we sort of dug this idea up. It hadn't been sort of talked about for maybe 3 or 4 centuries. And we actually applied it to a completely different problem, a free boundary problem. And it was only after applying it to this free boundary problem that we realized that we had the proof in this situation as well. So maybe let me try to address your question about why you can't do non-isolated singularities. This epiparametric inequality, we can prove for non-isolated singularities. But what it requires is that your surface can be written as a C1 alpha graph over your blow-up. You can do that with an isolated blow-up by this theorem. Away from the origin, you're flat. And so that means that you must be C1 alpha. When you have a non-isolated singularity, away from the origin, you're not necessarily flat. And so you're in trouble. So we can basically get almost all the way there. But then we're stuck at sort of the last final application. And that's where we really want to go. It's been an open question as to whether or not the blow-ups, these tangent objects, are unique at non-isolated singularities. This has been open essentially since the early 80s with these 2 papers. And we hope that because our approach sort of doesn't require on having a PDE parameterization, but rather just a C1 alpha parameterization, that we should be able to make some sort of extra progress towards this. Okay. So I'm about to change tacts, but are there any questions on the minimal surface front?
I can ask a basic question. So
Yes,
you
please.
say that U has continued in many blow-ups. I just don't know what it means. So what do we mean when U has? I see the picture of the blow-ups, but I don't see where the U takes.
Let UR of x be equal to U of Rx. And then if you zoom in,
Okay.
there's still a compactness result. And at different RJs, you get different zero homogeneous functions. And you really get a continuum of different zero homogeneous functions. Right? I mean, how does this proof work? He does this, and then he repackages it as a harmonic map.
I see. Okay.
It's really cool. Yeah. Okay, great. So let me completely change tacts for a second, and then hopefully at the end of the talk, if you'll let me, I'll wildly speculate and try to sort of tie together the 2 threads. This also means that if I completely lost you on the minimizers front, then maybe you're willing to come back to me for 5 or 10 minutes on this other front, because I'll start at 0 again. So now I want to go back to the question 2. When do critical points regularize like minimizers should? This is inspired by this weird example of Tristan Riviere, right? And to do this, I need to introduce, so this is part 2, which I'll call regularization, or lack thereof, of harmonic measure. So I need to introduce harmonic measure, so here's a little primer. You start with some domain, omega n Rn. You pick a point, x, and you run a Brownian motion until it hits the boundary. And now if I have some subset of the boundary E, the harmonic measure with a pole at x of E is the probability that a Brownian motion starting at x exits first in E. Okay. I'm not a probabilist, so let me switch to PDE, if you don't mind, because I pretend to know PDE. What you can do is you can study what's called the Dirichlet problem. You want to find some U, so find U such that the Laplacian of U is equal to 0 in omega, and U equals F on partial omega for some given F, which is a continuous function, let's say, on the boundary. So physically, what you should think of is I have some plate. I heat the edge of the plate to be some temperature, not necessarily uniform. And then I ask what's the temperature at this point in the middle of the plate. That's given by the value of this function at that point. So this is the temperature distribution at equilibrium. And then we'll call this u sub f at the point x is given by integrating f against the harmonic measure. So f of q d by q. Okay? This is the idea. Okay. So before I sort of talk more about it, you might want to ask, why study harmonic measure? Okay, there are some people in the audience that I don't have to convince because they've spent their lives studying harmonic measure, but maybe there are other people in the audience that I have to convince a little bit. So harmonic measure in dimension 2 has lots of interesting connections to conformal maps. It obviously has this connection to probability, and there are probabilists who care about conformal processes who think about this a lot. For me, harmonic measure is very interesting because it's connected to the Dirichlet problem, to this. So here's a very beautiful theorem, which summarizes about 30 years of work, starting from Dahlberg and Koenig in the 1980s, and ending with Hoffman and Le in 2017. There exists a C such that the L2 norm of the solution to the Dirichlet problem in the whole space is bounded by the L2 norm of the data on the boundary. Okay. If and only if harmonic measure is mutually and quantitatively absolutely continuous with respect to surface measure, which is the Hausdorff measure restricted to the surface, but if you don't care about Hausdorff measure, really think of the surface as being smooth. And yeah, this is just surface measure in the sort of traditional sense.
Surface being the curve you're drawing over there.
Yes, this is partial omega, right?
So are there any assumptions on the smoothness of the boundary? Or?
I need, for partial omega, there's only one assumption, to be quantitatively n-1 dimensional. So you can see how maybe if I had a sphere, I wouldn't want to then look at the sphere and a line, right? Like somehow these two parts of the boundary look differently and you shouldn't really be able to solve the Dirichlet problem here. And now because everything is quantitative, I need a quantitative notion of this. So for those of you who work with it, the notion is Alfor's regular. And it basically asks that the measure of a ball of radius r centered on the surface is approximately r to the n-1, where the constants here should be independent of the center and of the scale. But don't worry about this. I mean, if you don't work with this, just really think about quantitative n-1 dimensionality. Okay? And this is a very important concept, right? What I'm asking is, take my plate, which I've heated to different temperatures, and now just like turn on and off your lighter at one point on the edge of the plate. Physically, this should mean that I don't change the temperature distribution very much. So if I can't solve this Dirichlet problem, I'm doing something highly non-physical. And that's a problem. And it's not the Dirichlet problem. Okay. Fantastic. We're doing great. Maybe it would help if I give you some examples. Say you start with this disk, and the pole is at the origin. Then the harmonic measure is simply equal to the surface measure, which is length in this case. But harmonic measure is a probability measure, so I have to divide by the length of the circle. Okay? It makes sense. You can equally hit any portion. You're equally likely to hit any other part of the boundary. If you start with a domain which is what's called a Lipschitz domain, so locally you can write it as a graph of a Lipschitz function, then harmonic measure is mutually absolutely continuous quantitatively with respect to surface measure. Harmonic analysts have a term for this. They call harmonic measure an A infinity weight. But really what you should think of is that sets with zero length have zero harmonic measure, sets with zero harmonic measure have zero length, and this is true in a quantitative sense. Again, everything is quantitative. And now, if you have a fractal, I'm bad at drawing fractals, so maybe I'll just draw the first iteration of a fractal, right? Because otherwise we'd be here all night. Then the harmonic measure is singular with respect to surface measure. So anything that has finite length has zero harmonic measure. Yeah, the harmonic measure lives sort of, I mean, you imagine these things sort of twist around and around and around and around and around, right, as you build more. The harmonic measure lives in the points where you had to twist infinitely many times this way and also twist infinitely many times that way. It's kind of crazy. But that happens to be most of the points on the snowflake. So, okay, so then it's legitimate to ask a question. How does the geometry of partial omega, this is terrible English, what does the geometry of partial omega tell us about, let's say, the Radon-Nikodym derivative, right? Sets that harmonic measure C and versus sets that sigma C's. And vice versa. If we know that this Radon-Nikodym derivative is nice, what can we say about the geometry of our domain? Okay? So here's a theorem which is due to Carlos and Tatiana from the late 90s, early 2000s. So under very weak topological assumptions on omega, very, very weak. For example, they're satisfied by the snowflake. I basically just don't want it to be disconnected or have cusps in the boundary, because these make solving the Dirichlet problem a pain. So weak topological assumptions on omega. Partial omega is quantitatively n-1 dimensional, so this is the Alford's regularity. Then the oscillation of the unit normal controls the oscillation of d omega d sigma, and vice versa. So if the unit normal is in C0 alpha, then d omega d sigma is a C0 alpha function. And if d omega d sigma is a C0 alpha function, then so is the oscillation of n hat. So here we have regularization. We're defining something in a very weak sense. This measure is defined by the Riesz representation theorem, but actually we get regularity, like in the case of harmonic functions that I wrote on the board earlier. Let me say that this has been generalized.
That regularity kind of at the boundary.
Yes, regularity, because interior regularity
It's an old theorem.
is an old theorem, exactly. This has been generalized to nonlinear PDE, the P. Laplacian. This is due to John Lewis and Kai Nystrom in 2004, and it was generalized to parabolic PDE, what's called the caloric measure, where you care not just where you exit the domain, but when you exit the domain. And this was my thesis in 2017. Okay, great. So we have regularization of harmonic measure, but I promised you lack thereof. So let me try to do that in the next 5 or 10 minutes. higher codimension. Say I want to play this game. Carlos and Tatiana tell me that I can characterize the geometry of a set, a codimension 1 set, by the behavior of PDE and the complement of that set. But you might care about not codimension 1 sets, codimension 8 sets. And you'd like to be able to say the same thing, right? So maybe what you should be thinking is here's some gamma, which is a Lipschitz or continuously differentiable curve. And it's going to be living inside of R4, let's say. Right? There's a big problem. The Laplacian doesn't see sets of codimension greater than or equal to 2. So going back to the Brownian motion, if you have a Brownian motion in R3, it won't necessarily hit a point, right? And the Laplacian and the boundary motion, they talk to one another. So
you want to change inequality?
Yeah, so I want to be very careful here. If a set is alpha's regular of codimension greater than... Oh. Sorry, I thought you were talking about this equal sign, which I do have to be careful about. If a set has infinite hn minus 2 measure, it's possible that the Laplacian can see it. But if it's like an alpha's regular set of hn minus 2, then the Laplacian won't see it. So the equality case here is a little bit trickier than I'm letting on. But, okay, certainly the curve in R4, I'm safe.
Sigma finite infinite or infinite infinite?
I think even if you're sigma finite, the Laplacian won't see it.
Won't see it, right?
Yeah, I think you have to have locally infinite
Yeah,
hn minus 2 measure in order for the Laplacian to notice you. It's a capacity argument. Okay. So what I'm going to do is the following. I'm going to look at the following operator, which I'll call L. And it's going to be negative div 1 over the distance from my set x to gamma to the n minus d minus 1 grad u. So what should you be thinking? The Laplacian is the divergence of the gradient. But I want to pull my Brownian travelers towards my higher codimension set. And this sort of acts as a gravity which does this. Okay? There are also lots of other choices you can make for this matrix, right? This is the simplest possible case.
n minus d is the codimension.
Yes, so I live, in this case, it would be 4 minus 1 minus 1, or 2. Okay? And this scaling is just the natural one. If you like play with the coefficients a little bit, you find out it has to be this. And notice that when d equals n minus 1, this is 0. So we recovered the case of the Laplacian. Okay? Great.
So this operator will give regularity on this set, hopefully.
Hopefully.
That's the idea of what you're
That's
saying.
the idea, yeah. So what you're trying to do is you're trying to solve LU equals 0 on Rn minus gamma, where gamma is this quantitatively d-dimensional, and maybe U equals F on gamma. And it turns out that if L looks like this, you can solve this. And so there's a harmonic measure, which I'll call omega L. Right? And this harmonic measure, it's the exact same thing. You integrate F against the harmonic measure on the boundary, and you get U. Okay.
There is a probabilistic interpretation of the process.
Yes and no. Yes, I can give you a dumb answer to your question, which is that for any matrix you put in here, I think by sort of abstract reasoning, there exists a Wiener process. Okay, the matrix maybe has to be smooth or something. There exists a Wiener process which is driven by the same matrix, and the hitting probability, you know, it's sort of the same picture as harmonic measure. Could I tell you in any way, shape, or form what the process looks like given this set? I have no idea. I just don't know stochastic PDE very well. But I think it's a really interesting question, and it will be even more interesting in about 5 minutes. Okay. So in 2017, Guy David, Josef Fenoy, who's a postdoc of Svetlana Meibaroda, and Svetlana Meibaroda showed that if you smooth the distance function, so instead of distance, you put a smoothed out version of distance here, then if gamma is a, let's say, C1 graph, then omega L is mutually absolutely continuous with respect to HD restricted to gamma. So it turns out that this operator, which is sort of the easiest instantiation, is a little bit too rough. The distance function is not C1, for example. So if you smooth out the distance function a little bit, and I can write that down for you if you really want to see it, then it turns out that, that you basically recover this result, or the forward direction of Koenig and Toro. If the graph is smooth, then harmonic measure plays nicely with surface measure. So here's where I enter the story. Guy and Svetlana knew that I had this result in my thesis, and they say, oh, you know how to prove the backwards result? Can you prove the backwards result? And I messed everything up. So here's the theorem. It's joint with Guy and Svetlana from earlier this year. There exists a C, which you should think of as depending only on the dimension and the codimension. Oh, sorry. I need for n minus d minus 2 to be strictly positive. And I'll tell you why in a little bit. But you should be thinking Lipschitz curve R4. There exists a C, which depends on n and d, such that for all d alphas regular gamma, right? Alpha is regular is the quantitative d-dimensional. There exists an operator L. L looks like this, but with a smoothed out distance, such that the harmonic measure with respect to L is comparable to the surface measure on gamma. So Carlos and Tatiana tell us that if this behaves nicely, then this behaves nicely. In higher codimension, pick the nastiest set you can think of, a four-cornered Hanner set in R4. I can come up with an operator which really looks like this. I just smoothed out the distance a little bit, such that the associated harmonic measure sees essentially every point the same. And if you allow me just a little bit more room to wiggle, if gamma is a C1 graph,
But you're supposed to set this alpha is regular, or not?
yeah, it's alpha is regular. For all alpha is regular gamma.
Okay.
So, but the four-corner Hanner set is alpha is regular. In particular, d could be a fraction. D could be pi in R10, if you so like. Right? As long as it's quantitatively pi dimensional, which is a thing that you can construct, I can come up with a matrix that does this for you. And if I have a little bit more regularity, if I'm a C1 graph, but definitely not smooth, then harmonic measure is proportional to surface measure. It's a corollary of the work of Carlos and Tatiana that harmonic measure and surface measure are only proportional if you're a sphere or a half plane. So in codimension 1, it's incredibly rigid. In higher codimension, there's no rigidity whatsoever.
Well, you can put the variation in the L.
Yes.
I mean,
So
the L is a variable.
yes, but I want to tell you, this L is C infinity outside of gamma and is comparable to the distance. So really I construct a function which I'll call d alpha, d of x, which is comparable to the distance from x to gamma, and d is in C infinity of Rn minus gamma, and then my operator is negative div 1 over d to the n minus d minus 1 gradient. So it's still a diagonal operator. I've done nothing. Okay, so I'm almost out of time. So if you'll forgive me, let me speculate wildly for a second. So what's the difference between this and this? Let me point out that in the codimension 1 setting, there is no known situation, no known operator for which we can make a statement that's even close to this, for which we can prove this type of comparability when the set is rough. Okay? So for example, there's no elliptic operator for which the measure is comparable to the H1 measure on the 4-quarter Cantor set. No known one. This is an open question. Secretly, underneath this theorem, there's an energy. And it turns out that critical points to this energy are domains which satisfy these conditions. And so,
Are the what satisfied?
are the domains that satisfy these conditions. Or maybe I should say domains that satisfy these conditions are critical points to this energy. The energy looks like this. You take the gradient squared, and you add the characteristic function of the positivity set of U. And these domains are positivity sets of critical points to this function. And if you assume a little bit of niceness, this Alfor's regularity, then really you're close to a flat point most of the time. You're close to a flat point most of the time. And you can basically apply the flat implies smooth argument that I was talking about before. But here, we're in a situation where there doesn't seem to be an energy that works nicely. It's sort of like the Tristan Riviere example. In some sense, you should think of this as being a critical point, but we're missing the directions in which you should vary the function. And so I think this is sort of the phenomenon that's going on right here, and this is a general phenomenon that I'm interested in. Anyway, I've taken way too much time of your time. Thank you very much for listening.
Questions? Where's the restriction n minus d minus 2 positive come in?
Yeah.
What's the question?
Where does this restriction n minus d minus 2 positive comes in? I'll write d for you, okay? Maybe here is okay, because it's sort of centralized. D is simply equal to 1 over x plus y to the n minus 2, d hd. This is having a gamma of y, and all of this has to be done to the negative 1 over n minus d minus 2. And in order for this function to be comparable to the distance function, you need n minus d minus 2 to be positive.
That's all?
That's all. You might ask, why this?
Yeah.
No idea. We have no clue what's going on. We were trying to prove the opposite of this result. We were trying to prove the converse. And so I was looking for barriers, for solutions to LU is positive or LU is negative. And I tried this, and I got LU equals 0. And yeah, this happened. So there's still a lot of investigation to be done.
Should we say anything about that critical case when it's equal to 0? Or
No, but that's a really good question. Yeah.
What is the operator error you construct?
Hmm?
The operator error you construct.
It's this diagonal operator, div 1 over this distance function, which I've written down, grad u. And then it turns out that for this distance, the distance is a solution to the operator. And this makes everything go. It's, Guy calls it magic.
I mean, how general does the function capital D has to be?
No, I've written d down for you.
I mean,
It's an integral.
I mean, can we give some more general?
Oh. The thing is that we just differentiated and got this result. We have no idea why it works. Maybe it works for lots of other functions, but we just have no clue. I mean, this is something that we really want to investigate. Whether or not this is, for example, generic, or if it's really just special to this particular D. It's a really good question. Yeah.
Thanks, speaker again.